Okay, you can begin now.
All right. So good day, everyone. So welcome to the live conversation. And I believe you can hear me. Can everyone hear me? Hello?
Hello, we can hear you.
All right. Yeah, thank you. So I'll be sharing my screen now. By the way, I'm John by name. So let me do that right away.
You can share your screen now. I've made you co-host.
Okay. So can you see my screen? So so today we'll be treating model fine-tuning, and when we say model fine-tuning, it's simply the process of adjusting a pre-trained model so it performs better on a new similar task. So this can be likened to a doctor in a medical procedure. That's already a doctor, but now he's being taught a new medical procedure or a new skill in a particular area. So when we say fine-tuning, you're fine-tuning an existing model to transfer learning, as in machine learning and model building. So in machine learning, what you do is you take an existing model or a pre-trained model, as it's been called, and you build on it. So also is fine-tuning. In fine-tuning, you utilize pre-existing models to enhance the knowledge for new task or novel task in specialized domain. So it is very important we do this because these large language models or these foundational models, they may not prove, they may prove insufficient when dealing with intricate or specialized subjects, such as a company's legal framework, for example. And when you are looking at uh, domain-specific applications of these LLMs, it might be so difficult, and that's why there's a need for fine-tuning. Generally, LLMs are trained on a wide variety of subjects, general subjects in all domains. So when we begin to use it for domain specific, they may not prove sufficient enough. And these domains may have technical terms that are related to them. They may have principles that are related to them. Take, for example, uh, a company like Dangote in Nigeria may have a particular aspect they want to use this LLM for. So they don't have the knowledge of their particular field or their particular company, and therefore there'll be need for fine-tuning in this process. So through the process of fine-tuning, LLMs can assimilate insights from customized examples. So when they are given their specified data sets, then with the knowledge or with the different layers of learning, they can easily assimilate the new and customized examples. And examples of such pre-trained models, we have BET, we have the GPT-3, we have the cloud. So these have already learned the general language representation from large data sets. And fine-tuning adapts this general presentation to the nuances of the specific task that is being worked upon, and such as sentiment analysis. Take, for example, now the BETS as an LLM. BETS on its own, BART, may not be able to perform sentiment analysis. And it cannot perform sentiment analysis actually. But when it is being fine-tuned, it can be fine-tuned to perform this sentiment analysis, and even such as question answering or sequence classification. And I want to talk of fine-tuning. So fine-tuning involves taking a foundational model that has been trained, as I said earlier, on a large data set. And this large data set has a whole wide category that cuts across everything from coding, um, language. From language, you can go into different areas, script writing, across all fields, arts, sciences, and even uh, various tax applications. And that's why you can easily take a GPT model and you can use it for language learning. You can take it and use it for several other activities. You can give it some questions like the previous studies that we looked at, where we looked at prompt engineering. You can easily prompt it and to give you answers without prior coding or without prior learning. So, but in fine-tuning, you take the foundational model and you perform some modifications to enhance the performance on a specific task or data set. So what it does is that you take the end goal, the end point of the data of the model, which is known as the head. So in the head, you remove the head, which is always task specific. You remove the head and you replace it with the specified data sets you want to train it on. So this gives the model a more streamlined approach, but with the previous knowledge, there is that ability to comprehend the last end. So similar to the machine learning uh, process I explained before, you can simply take the whole model, then remove the last layer and attach this task specific process you want. And if you look at it, here we have a foundational model, which can be anything, any LLM. It could be BETS, it could be GPT, it could be Cloud or whatsoever. Then you remove the head and you attach the last classification head. So if, for example, you want to do a uh, sequence classification, all you have to do is to remove this classification head and attach a sequence classifier. If you want to do, you want to, whatsoever you want to do, it could be a classification, it could be sentiment analysis you want to do. So all you have to do is just to remove the head and allow. So most of it in foundational models, you just have to take away the last layer and add a more specific layer you need. And to go it to process this, there are some processes that needs to be done, such as the collection of labels data, the analysis of the labels data, the Sorry, can you hear me now? I didn't know I was muted. Hello?
Yes, you're audible now.
Okay, thank you. So I didn't know I was muted. Let me just go a step backward. So we've covered the essence of fine-tuning. So I said fine-tuning is the application of pre-trained model. So fine-tuning is actually the process of adjusting pre-trained model so it can perform better on new and similar tasks. So such more like teaching a doctor, an already experienced doctor, a new medical procedure that's they need to just learn just in a particular area. He's already a doctor, but you just need him to perform on certain skill sets that have not been in his arsenal before. So fine-tuning, as I've said, is closely related to transfer learning, and it utilizes existing models to enhance knowledge for novel tasks or domain-specific tasks. So when we ask why fine-tuning, um, fine-tuning is actually used when we want to work in a domain-specific area. Take, for example, now I gave an instance of Dangote. Now, in Dangote, you may not, when you want to use an LLM, the LLM being trained on a large variety of data may not have specific knowledge of all that's been done in that company. So therefore, to use it, there'll be need to train it on the company's data sets and allow it to adapt to that particular field so that it will be able to give useful information. So when the application of pre-training proves insufficient, then there is a need for fine-tuning. Unlike normally when you were taught the zero prompting, the single prompting in a general LLM, you can simply give it a question and the LLM, such as GPT, knows what to do. That's when there's a general question. But take, for example, a law-specific area, a domain-specific area, there'll be need to fine-tune it. So through this process, the LLM can assimilate insights from customized examples. And examples of these pre-trained models, we have the BET, we have GPT-3, we have Cloud, and we have several others. And they've learned the general language representation from large data sets. Most of these foundational models have been trained on billions of data sets, and they are able to adapt in different ways. But for a specified application, fine-tuning will help these models to adapt to the general representation of the analysis of those specific tasks they are working on, such as sentiment analysis. And as we look at bits, for example, bit analysis, but when it is being fine-tuned, it will be given the ability to perform sentiment analysis, question answering, or sequence classification. So when I said the steps involved in fine-tuning, so to fine-tune a foundational model, there'll be need for parameter modification to enhance performance on a specific task or data sets. So when we have a foundational model or LLM, such as BETS, such as GPT or Cloud, whatsoever it may be, and to fine-tune it, all you need to do is to remove the last layer, which is always known as the head of the model. So you remove the last layer of the model or the head of the model, and you replace it with whatsoever task-specific application you want it to perform. If you need if you need to perform a classification task, all you need to do is to replace it with a classification aid. If it's sentiment analysis you want to perform, you simply replace it with a sentiment analysis aid or whatsoever task-specific application you want to perform. So this gives the model a more narrow specific approach to approach that problem, and it gains more insights into the scope you want it to do. So you just remove the last layer and replace it with whatsoever layer you want to use. And in fine-tuning a model, the processes involved include the collection of the labeled data sets. So just like every machine learning model, you need to collect a data set which has been labeled. So the model will learn from it, the patterns, and will be able to predict instances. So is the foundational model. The model, after you've collected your data sets, you need to be able to select your hyperparameter. So in this process, you collect the label data set any from any domain you want to use. It could be sentiment analysis, it could be classification task, it could be whatsoever. So you get your data sets, then you also go through the process of hyperparameter selection, then model adaptation. So when we talk of model adaptation is actually the process of removing the last layer of that model and replacing it with this task specific aid you want to process. And there are several there are several models that are out there that can be used for these processes. But when we talk of open AI, which we might not be using today, but I'll just give an instance of it. So OpenAI has a way of dealing with this model adaptation. So it has an under the hood process that handles all of this. So you just need to define what you want to do by calling the fine-tuning class. So you use the OpenAI.fine-tuning and you define it. You can check it up in the OpenAI library, and their documentation. So for the evaluation and iteration, you go ahead to evaluate and iterate. Then you also implement the model and further train. So similar to every machine learning process, the process goes almost the same way. So now for pre-processing, prior to embarking on fine-tuning, it is essential to pre-process the data in accordance to the API's specification. For example, now for the OpenAI, which I mentioned before, OpenAI makes use of the JSON L format, that is the new line delimited JSON format. So when you're processing a data for using the OpenAI LLM, which is GPT, so all you need to do is to take and ensure that data is in JSON format. So depending on the type of API you're working with, you need to apply those preprocessing steps to it. Then other preprocessing steps you can apply will include removing of duplicates, splitting the data, shuffling the training data, then creating the OpenAI JSON format class if you're working with OpenAI. And one other thing we're going to look at today as well. So when we get to the coding section, we want to look at the dynamic padding. So when we talk of dynamic padding, it's actually a common practice in frameworks like TensorFlow and PyTorch. So it is used to enhance the training efficiency, and it is a technique in batch processing. So this adjusts the padding of variable length sequence within each batch to match the length of the longest sequence. So instead of padding the entire data set at once. So you may have some data sets that are, take for example, with maybe 100 tokens, let me use 20 tokens or 36 tokens. Then you have another data set you have another sentence of 20 tokens. You have another sentence of 15 tokens. You have another one of 50. So when you want to pad, there are other ways you can do it. You can either truncate to a particular size, or you can allow it to adapt to the longest token. So if you have the longest token of 50 in a particular sentence, and you have another one of 36, you are going to pad the 36 to have 50 tokens by adding several zeros or new tokens, depending on what you want to use to make it 50 tokens. So if we have a data set that has so many tokens and you want to batch all of them and pad it together, it's not going to be efficient for the machine to handle at once. So using dynamic padding allows you to pad it batch by batch, in the sense that for each batch, take for example, you have 30 sentences per batch. It is the longest sentence or the longest token among that 30 sentences that is going to be padded to. So every other one will be padded to it. And if you have another batch with 20 tokens, every other one will be padded to 20. So dynamic padding offers efficiency by reducing the computational load. It also offers flexibility by allowing processing of variable length sequences without discarding or severe truncating data. Then it also increases the performance of the model by giving it faster training time. So all of these are the essence of dynamic padding. So let's move on. So for today's class, as I said, we're not going to be using the OpenAI library, OpenAI API, but instead we're going to be using the Hugging Face library. So Hugging Face is an open source library that offers so many advantages. From tokenizer, you can easily tokenize this in the Hugging Face library. You can also get access to a variety of large language models. Then you also have access to treasures of data sets, and you have access to all of this for free. Then the Hugging Face dataset library simplifies the process of downloading and catching a dataset from the hub. So you can easily download from the hub. You can create an account. Let me show you that. So here we have, can you see my screen? So here we have the Hugging Face library. Let me load that up. So in the Hugging Face library, you can actually have access to several data sets as well. Then apart from that, there are several models you have access to. So here you can see the models. There are different models you can have access to. When you look at it, you see you have for image classification. It could be image segmentation, image to text, image to image, text. So you have access to a whole variety of models. Then for the data set as well, there are several data sets you have access to, such as the IMDb data set. You have access to matrix, a whole lot of them, and you can just you can access it through their API. You don't need to download it. So it simplifies the accessing of this data sets from their API. Let me go back. So for this live coding session, we're going to be making use of the Microsoft Research Paraphrase Corpus. Is a data set we can also obtain from the Hugging Face library, and it is used to determine whether another sentence is a paraphrase of the previous sentence. And for dynamic padding, I've explained what dynamic padding is. I said dynamic padding is when you want each batch to have the same padding. So you pad it batch by batch. And luckily, the Hugging Face transformer class provide us with dynamic padding. So you don't need to hard code it from the beginning. And it can be found in the data collector with padding class. So when it has been instantiated, it takes a tokenizer as an argument. So to determine which padding token to use and whether the model expects padding on the left or right of the input. So you can either pad on the left or the right. So when you pad on the left, it's like when you justify to the left or you justify to the right. And it handles all the necessary padding. Let's move on. So before we move to the class, to the coding, these are some technical terms that will be used that I've used already. So say tokenizer. Tokenizer is just like it's converting the words into similar parts and creating a code the computer can understand and work with. So it's like giving numbers to alphabets. Then models, we know what models are to be the brain for computing. So this allows them to learn and make decisions based on information they've been fed. Then the data sets. Data sets, you can think of a data set as a textbook for computer models. So these are just large collection of data related to a particular purpose. So you have data sets on sentiment analysis, you have data sets on image classification, and so on and so forth. So then the batches are small, evenly divided parts of data that the AI looks at and learns from each step of the way. So when we say truncating as well, truncating refers to shortening longer pieces of text to fit a certain size limit. And truncating is actually an important step in preprocessing because it helps to optimize the memory. Then padding. Padding is adding extra data to shorter text to reach a uniform length for processing. So it can be the opposite of truncating. Then bits. Bits is the model we're going to be making use of today. And it simply means bidirectional encoder representation from transformer. This was developed by Google in 2016. So it helps the model is able to learn from previous sentences. So it's able to look both ways from that word bidirectional. Then fine-tuning. Fine-tuning is a process of adjusting a pre-trained model so it can perform better on a new and similar task. So that said, we'll be moving on to the class today. So for the setup, most of our codings are going to be done on Colab for ease and so that everyone can be carried along. All right. So give me a minute. So first, we're going to start by importing the necessary libraries we need. We're going to be making use of, since most of our coordinates are going to be in PyTorch, we can start by importing Torch. Then we also import the data set as well. All right. So we're going to start by loading the data sets. So from data sets, so this data sets library is going to be from the Hugging Face resource that I mentioned then. So there might be need for us to install it if it's not supported on Google. So it is a library on its own. So from data sets, we're going to import. Let me install that on a different, since it's a class on its own. So import load data sets. So load data sets is what we're going to be using or we're going to use to load the data sets. So it's a class. All right. All right. All right. So we need to install it. So we can install it since it's not here. So we're going to just do pip install datasets. So this will help us install it. And while it's going, when we install it, we'll have to restart the section for it to instantiate. So most times on Google Colab, whenever you install a dataset, you might have to restart the whole section. If not, it will not still see. Let's see. All right. This time around, it's saw it, so we can continue. Right. Okay. So, fine. So now we can load the dataset from the hub. So now let's just give an instance. Let's get the raw data. Let's load the Microsoft Research Paraphrase corpus. So that will be raw data set. So the load data set is a function. And then this MRPC is under the glue function. I mean the glue principle is actually what is used to is a guideline or a benchmark that can be used to determine is actually general documentation and a guideline for most data sets. So you can actually check it out. Let me try to open it up here. So the glue benchmark is actually a general language understanding evaluation. So it's a collection of resources for training, evaluation, and analyzing natural language understanding systems. So it's what we're going to make use of. So that benchmark is what is guiding most of these data sets. And they've actually been reviews of some of these things. Like we have the super glue, which is an enhanced aspect of it. So let's go back to our data sets. So we can actually view this. Let's check it out. So what it's doing is actually is loading it directly from the Hugging Face library, and you see it has actually downloaded it. And when we examine it, we're going to see that the dataset is actually a dataset dict object, and it contains a training set, it contains a validation set, as well as a test set. So this set contains different columns. If you look at it, we have the two sentences, sentence one and sentence two. As we've seen from you can check out the MRPC documentation. There are two sentences. One is assumed to be the paraphrase of the other, more like a summary. Then we also have the label. Then we have the index. So the label is going to signify whether it is actually a paraphrase or not. So this is 1 or 0. Then the index is simply the index to hold that data set. The one other thing we can see from here is for the training, we have 3,668 rows. Then we also have 408 rows in the validation. Then for the test, we have 1,725. So this actually is a good, a substantiable data set that we can make use of. So we can actually check out some of them. Let's check this out. Let's check out the train sets. So let's see. Let's just see a subset of it. Let's see the first one. So if you look at it, here we have the first sentence, sentence 1, and we see a sentence. Then we look at another sentence, sentence 2. Now, if you compare these two sentences, the first one says, and Rosie accused his brother, whom he called the witness, of deliberately distorting his evidence. Now, the second sentence here says, referring to him as only the witness and Rosie accused his brother of deliberately distorting the evidence. So now I want to know, if you look at it, the label is labeled 1 here, and the index is 0 as we've looked at it. So actually, the labels are, the way they have arranged it, is 0 corresponds to not equivalent. Y1 corresponds to equivalent. And this is actually summarizing, sentence 2 is summarizing sentence 1, as we've seen. So we can check out another one. Let's check out virtual data sets. And let's check out class 15, index 15. All right, so let's look at this one now. Sentence 1 shows that Ruda was most recently senior vice president for the developer and platform evangelism business. And sentence 2 shows that senior vice president Eric Ruda, formerly head of the developer and platform evangelist unit, will lead. So if you look at it, both of them are not saying the same thing. This is talking about Eric Ruda as the senior vice president for developer and platform. But this is talking about senior vice president Ruda, formerly head of developer and platform evangelist units, to lead a new entity. So they are not actually saying the same thing, though they're actually talking about Ruda. So the label here is 0. So this is a whole set of labeled data sets. And when we train a large language model on this, it can be used to streamline the process just for this sole purpose of determining whether a sentence is a paraphrase of another. So, and when we look at it, we can further examine the data sets by checking out the features of the data set. Since we're dealing with a data set class, so let's check out the features. So when we look at it, this is necessary when we want to perform preprocessing on the data set. When we look at it, sentence 1 has a value type of string, while sentence 2 has a value type of string as well. So we might need to preprocess it, and probably want to transform it to tensors or want to split it or whatsoever. So we can actually perform all of this. Then the label, if you look at it, the label is actually a class label type. So it's easy for mapping. We're going to be able to easily map it because it's a special type of class, whereby when you want to map it, what goes on behind the hood, we just map 0 to 1, that is 0 to correspond to not equivalent, while 1 corresponds to equivalent. Then the index as well. The index is integer, so we don't need to perform any preprocessing on that. So the labels, we don't need to also perform any preprocessing on that as well. We can go ahead with that. So now let's move on. Let's move on to the preprocessing and let's check out some things. So preprocessing, one of the steps in preprocessing I mentioned is we can either split the data sets, we can tokenize the data sets, and a whole lot of it. So we're going to make use of the library auto tokenizer from the Face Transformer library. So with this, um, we need to define the model we want to make use of. So there are actually different types of models, and for this, we're going to make use of the bet-based uncased model. So this is also an uncased model, such that if you look at it, it's been classified bet-based uncased. The uncased there shows that the head is it's more like they've removed the casing, the head. We have another type of model which is a cased bet model. So that's it treated as a specific task. So for this, for making use of the bet-based uncased, so we can define our tokenizer as well as the auto tokenizer from pre-trained. Time is no longer on our side, so I'll rush things up now. So with this now, let's get our first sentence. So let's define the tokenized sentence one. So for this, we're going to pass this to the tokenizer. We're going to pass the data set. So let's just pass a single data set for now. I mean a single sentence. So then let's also tokenized data set sentence two. So what this is doing is we're actually taking this first sentence and we're taking the second sentence and we're passing it to the tokenizer to token it for us. So we have two sequences there. Now, this might not actually be enough to do that, but let's want to just examine what is going on under the hood before we start handling several classes tokenizer. Sorry. So now let's pass in our own. So when we check the inputs, we'll see that it has actually transformed. Oh, sorry, we use inputs. Let's use inputs here. So it has actually transformed into tokens. So this is the first sentence here. These are the tokens for it. Yeah. So we can see that transforming into tokens are just transforming it to what the model will understand. And we can also transform, we can check it out. We can check the IDs. Is a bidirectional process. So what we see that you see that the model is able to convert these tokens, convert these IDs of these tokens, and is able to convert them and understand. Because why isn't this model already from these checkpoints that we defined here? These bits based on case. So is able to understand the different um the delimiter partitioning and every other thing, because that's one of the processes of pre-processing that we're going to look at as well. Let's look at another example. Let's look at it. Let's check another one. Let's see. Let's check out inputs. Is equals to So actually, because of time, we're not able to do much on that. So, but on and try to process the data set accordingly. So what we're doing now is we're passing it into all of this. Then we are padding it and we're also truncating it as well. So what this is going to do is it's going to pad those sentences that, take for example, look at the first sentence, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So these are actually the same. But take for when we have two sentences that are of different lengths, the padding equals true is going to make it of same length. Then truncating is, there's a default value for truncating, and let's look at it. Truncation. So the truncation strategy is none. There's actually a default value for truncating, and you can check it later on. And but you can also set your value for truncation as well. So let's run this. Then one more thing we can do as well is to put this in a function to tokenize the data set. So this will make the whole process easier. So when we pass in this, now we can now easily map this to whatsoever data sets we want to be working on. So what this function does is we define a function that takes in a sentence, an example sentence. So this example sentence will contain both the paraphrased and the original sentence, and it's going to return the tokenized examples. It's going to return it. It's going to pass it into example 1 and example 2, and it's going to return the tokenized examples. Then we can then map this to the whole data set. Instead of doing it one by one, we can then take this function and map it. And because of the structure of the data set, we can easily use the map function. So when we do tokenized data sets, let's change this. So we've been able to map it successfully. So this way, the dataset library applies this preprocessing step to the whole data set for each sentence and paraphrase. That is for each sentence 1 and sentence 2 in the whole data set. We're going to map this. We're going to map this to this function, and it creates a seamless way of doing it. We have several. We have about 3,000, as we've seen from here. We have about 3,000 data sentences. So instead of doing it one by one, we have this to just answer it for us. So it's working. So it's been able to map it, and if you look at it, It has marked the training, each of them. Now, the last thing we can do today is to use the dynamic padding. I don't know if time will still permit us, but let's work with it. Let's quickly work on that. All right. So for the dynamic padding, I told us initially that dynamic padding, we can actually get it from the data collector with padding class. So from the data from transformer, we're going to import, okay, from transformers. So while that is loading, so let's find that. So pass the tokenizer into this. And so this class is going to help us with the dynamic padding, and it is done under the hood already. It is under the transformer class from Face. So we don't need to be worried about that. Let's just check it out. Okay, let's check out a sample and see how it works. So let's see a sample. So let's just take a small sample. Let's take the first 7 sentences. And we're going to iterate this with a dictionary. If you look at it, the type of the format of it is a data dict. It's a data dict here. So with a key and a value pair, a dictionary actually has a key with features, then the value as well. So we can set this to take what we need, because we don't actually need all the columns in the data sets. So key value for key value in samples dot items. Dot items is used to grab the key and value in the dictionary. If key not in, so we're going to define a list where of the ones we need. So index. All right. So what this does is we're only selecting the index, which is all we need, then the first sentence and second sentence. We want to pad them together. So when we check, okay, I'm having an error. Oh, dot items, sorry, dot items. All right, so fine. We can check the length of it. Let's just use a list comprehension. So length of X of I for high samples inputs ITS. So if you look at it, they have very length. 1, 2, 3, 4, 5, 6, 7, 8. The 8 sentences we're passing are very length in that class. Now, once I apply dynamic padding to it, as I said, what dynamic padding is that it's going to pad all of them to the longest sentence in that batch. And here we have the longest sentence in the batch to be 62 or 67 actually. So let's try it out. Now let's say the batch is equals to data collector. And we're going to pass in the samples. So now let's check it out. We're going to check out the key and value of the shape. So we're looking for the value of each of the shapes in this. Now look at it. So the input ID, we have the first one, 67. So this is the row by column. And look at it, the first one is 67, which is very correct. The second one too has been increased to 67. The third one, so all of them has been given the same size. And this will help. This eye is going to work per batch. Let's take another one. Let's just consider one more, just to show you. Then consider, here we have 67. Let's consider the first from 8 to let's say 16. All right. So you see this batch, the longest 61. So every batch here will be 61. I mean, every sentence here will be padded to 61. So that's how it works. Dynamic padding. So when we are feeding this into the model eventually, and we apply this data collector class, it's going to pad every sentence based on the length of the longest sentence in that batch. And this will allow the model to work efficiently and faster. So before we end, by next week, for the next class, we're going to work starts from the fine tuning. But before we end this, is there any question? Anyone? Any question? All right. You can type it in the chats as well. All right. So if there are no questions, we may end it today. Okay. So, all right. So we'll meet. Okay. So see you next week, Friday.